In 2020, on the outskirts of Ezhou in Hubei province, a heavy industry corporation named Hubei Zhongxin Kaiwei made an unprecedented operational shift. Originally a major cement producer, the company diverted a massive capital investment of 4 billion yuan, roughly $600 million, to construct two monolithic structures rising 26 stories above the Yangtze River basin. To the untrained eye, these towers resemble residential high-rises or office complexes, but they are actually the world's largest single-site livestock production facilities. This project represents a fundamental challenge to biological physics and traditional agronomy. Conventional agricultural science dictates that livestock requires horizontal dispersion to manage thermal loads and prevent cross-contamination. Concentrating 650,000 animals within a sealed vertical concrete environment creates immense engineering pressure regarding ventilation and thermal regulation. Skeptics argued that placing this much biomass in a confined vertical shaft would make disease control impossible, as the ventilation systems could essentially act as a highway for airborne pathogens. Yet, the operational data suggests a different reality. By integrating the farm directly with their existing cement plant, the engineers utilized waste heat from the kilns to regulate the internal climate, turning an industrial byproduct into a critical life support resource. Today, this facility achieves a staggering output of 1.2 million pigs annually on a land footprint that is only 5% of what a traditional open-air farm would occupy. This raises a critical question for modern engineering. How did they solve the logistical nightmare of moving tons of feed and waste vertically to turn a cement block into a high-efficiency biological machine? We will analyze the mechanics behind this massive structure right now. The pig farming complex in Ezhou is organized as a vertical production system divided into 5 main functional sections. Each section is designed to control a specific variable in large-scale pig production, including land use, disease risk, labor input, and energy consumption. The first and largest section is the animal housing zone. Each of the 26 floors is assigned to a fixed growth stage, ranging from nursery pigs weighing under 25 kilograms to finishing pigs approaching 110 to 120 kilograms at market weight. A single floor covers approximately 25,000 to 30,000 square meters of usable area. Around 60 to 70% of this space is dedicated to standardized pens arranged in long parallel rows. Depending on growth stage, each floor typically houses between 10,000 and 20,000 pigs, with stocking density fixed by pen dimensions rather than adjusted manually. Across both towers, the system maintains a standing population of roughly 650,000 pigs at any given time. The second section is the vertical transport system, which replaces roads, trucks, and internal corridors used in conventional farms. The towers are equipped with multiple industrial freight elevators, each rated at approximately 40 metric tons. One elevator cycle can transport 60 to 70 adult pigs or several tons of feed and equipment. Animals are moved between floors only at predefined growth milestones, usually every 3 to 4 weeks. All movement follows a one-way flow. Pigs move upward during growth stages and downward only once for exit. Feed, animals, and waste use separate elevator shafts to prevent cross-contamination. The third section is the environmental control system, which enables high-density housing without relying on open ventilation. Each floor operates as an independent air zone connected to a centralized ventilation network. Fresh air passes through multi-stage filtration systems capable of blocking fine particulate matter and airborne pathogens, including viruses associated with African swine fever transmission vectors. Airflow volume is calculated based on animal weight and metabolic heat output, often exceeding 200 cubic meters of air per hour per pig on finishing floors. Air pressure is regulated so that leakage always flows from cleaner zones toward dirtier zones, limiting vertical spread of pathogens. Temperature is maintained within a narrow range of approximately 20 to 26 degrees Celsius, improving feed conversion efficiency and reducing thermal stress. The fourth section manages feed input and waste output. Feed is stored in bulk silos at ground level, with total storage capacity measured in tens of thousands of tons. Feed is transported upward through sealed pipelines using screw conveyors and pneumatic pressure systems. Feed formulations vary by growth stage and are adjusted automatically based on real-time consumption data collected from feeding sensors. Waste follows gravity downward through sealed drainage channels. Manure and wastewater are processed in underground anaerobic digestion systems, generating more than 100,000 cubic meters of biogas per day. This energy is converted into electricity and heat, supplying a significant portion of the farm's internal power demand. The final section is the control and human interface. The entire facility is monitored from a centralized control room that receives data from over 30,000 sensors distributed throughout the towers. These sensors track temperature, humidity, airflow rates, feed intake, animal weight trends, and equipment status in real time. Human labor is focused on veterinary supervision, system diagnostics, and maintenance rather than manual feeding or cleaning. Compared to traditional pig farms, labor input per animal is reduced by more than half. By structuring the farm as a vertically integrated system with fixed functions, controlled airflow, and one-way material movement, the facility operates as a biological production line rather than a conventional livestock farm. Once infrastructure and environment are controlled at this level, biological growth becomes the main performance variable, setting the foundation for the production outcomes discussed next. The pigs raised inside the Ezhou towers are not local backyard breeds. They are commercial hybrid lines commonly used in large-scale pork production across central and eastern China, especially in provinces such as Hubei, Hunan, and Shandong. These hybrids are primarily derived from Landrace, Yorkshire, and Duroc genetics. Each breed contributes a specific advantage. Landrace provides fast growth and strong reproductive traits. Yorkshire adds robustness and feed efficiency, while Duroc improves muscle development and meat quality. Combined, these genetics produce pigs that grow quickly, tolerate confined environments, and deliver uniform carcasses demanded by industrial processors. Piglets enter the system shortly after weaning, usually between 21 and 28 days of age, with an average body weight of 7 to 8 kilograms. Before arriving at the towers, they are raised at external breeding farms and undergo health screening. Once admitted, the production cycle becomes closed. No additional live animals are introduced, and piglets move through the system as synchronized batches. This approach became especially important in China after African swine fever spread rapidly across provinces through animal movement and informal trading networks. Growth inside the building follows a fixed biological schedule. Nursery pigs are housed on lower floors, where temperatures are kept slightly higher to support digestion and immune development. At this stage, average daily weight gain ranges from 350 to 450 grams. As pigs grow, they are transferred in groups to grower floors, where daily gain increases to around 650 to 750 grams. In the final fattening phase, pigs commonly gain between 800 and 950 grams per day. Under these stable conditions, pigs typically reach market weight of 110 to 120 kilograms within 160 to 180 days from weaning. Feed management drives this performance. Nursery pigs receive high-protein diets exceeding 18% crude protein, formulated to support gut development after weaning. As pigs mature, protein levels are gradually reduced while energy density increases. Finishing diets usually contain around 15% crude protein, optimized for lean meat deposition. Feed is delivered in multiple small portions throughout the day rather than large meals. Across the full cycle, feed conversion ratios generally range between 2.5 and 2.7 kilograms of feed per kilogram of live weight gain. Water intake is monitored alongside feed. Finishing pigs typically consume between 8 and 12 liters of water per day. In practice, changes in water consumption often alert staff to problems earlier than visual checks. A sudden drop in water intake may indicate heat stress, digestive issues, or the early stages of illness. Disease prevention is built into daily routines rather than treated as an emergency response. Veterinary teams follow structured vaccination schedules commonly used in industrial pig production in China. Piglets are typically vaccinated against classical swine fever, porcine circovirus type 2, and other endemic diseases during early growth stages. Additional vaccines, such as those for foot and mouth disease or PRRS, are applied depending on regional risk assessments. Vaccination is carried out floor by floor, with pigs handled in small groups to minimize stress and mixing. Daily biosecurity practices are strict and highly procedural. Workers must follow shower-in and shower-out protocols before entering animal areas. Clothing, boots, and tools are assigned to specific zones and are not shared between floors. Floors operate on an all-in, all-out principle, meaning that once a batch of pigs leaves a floor, the entire area undergoes cleaning, high-pressure washing, and chemical disinfection before new animals arrive. Disinfectants are applied using automated spraying systems and handheld equipment, targeting floors, pen dividers, and drainage areas. Airborne disease prevention relies not only on filtration but also on sanitation. Technical staff regularly disinfect ventilation inlets and service corridors. Equipment such as feed lines and water systems are flushed and sanitized on scheduled cycles. Waste handling areas receive additional treatment to reduce microbial buildup. Health monitoring focuses on early detection rather than mass treatment. Sensors track feed intake, water consumption, movement patterns, and weight gain at the group level. If growth slows or behavior changes beyond expected ranges, veterinary staff inspect the affected area. Instead of routine antibiotic use, interventions are targeted and limited. This approach reduces antimicrobial resistance and keeps production more stable over time. Mortality rates in well-managed systems like this are typically kept below 3% across the full production cycle. While losses still occur, the controlled environment prevents sudden spikes associated with heat waves, cold stress, or uncontrolled disease outbreaks that affect many traditional farms. Because health, growth, and output are tightly synchronized, slaughter schedules can be planned months in advance. This predictability is especially valuable in China, where pork remains a staple food and supply disruptions have wide economic impact. By combining standardized genetics, automated nutrition, and disciplined daily biosecurity routines, the system turns pig growth into a managed biological process. Variation is reduced, risks are contained, and production remains stable. With biology largely under control, the next step is to examine what this stability means in economic terms and whether the model can justify its massive upfront investment. Once pigs leave the towers, they enter a very conventional market. There is nothing exotic about where they go or how they are used. The animals are sold primarily to large slaughterhouses and meat processors in Hubei and neighboring provinces in central China. From there, the pork flows into the same channels that supply supermarkets, wet markets, food processors, and restaurant chains. In other words, pigs raised in a 26-story building end up on dinner tables in exactly the same way as pigs raised on traditional farms. Most pigs are sold at market weights of around 110 to 120 kilograms. In recent years, live pig prices in central China have fluctuated widely, but a typical range has been roughly 14 to 20 yuan per kilogram, depending on market conditions. At those prices, each pig generates between 1,500 and 2,200 yuan in gross revenue. With an annual output of about 1.2 million pigs, total yearly sales can easily reach several billion yuan during stable market periods. One of the key advantages of this system is consistency. Traditional pig farms are highly exposed to weather, seasonal disease pressure, and feed supply disruptions. Output can swing sharply from one quarter to the next. In contrast, the vertical farm produces a steady, predictable flow of pigs throughout the year. This makes it attractive to large buyers who value reliable supply over short-term price spikes. Long-term contracts with slaughterhouses help reduce price volatility and stabilize cash flow. Beyond pork sales, the project generates additional benefits that traditional farms rarely capture. The waste produced by hundreds of thousands of pigs is not treated as a disposal problem but as an energy resource. Anaerobic digestion systems convert manure into biogas, which is used to generate electricity and heat for on-site operations. This reduces energy costs and partially insulates the facility from fluctuations in power prices. Solid residues from digestion are processed into fertilizer products that can be sold or reused in nearby agricultural areas. Cost structure is where the comparison with traditional farming becomes clearer. The upfront investment is enormous, far higher than building conventional barns. However, land use per pig is dramatically lower, an important factor in densely populated regions of China. Labor costs per animal are also significantly reduced, since automated feeding, monitoring, and waste handling replace many manual tasks. Feed efficiency is higher due to stable conditions, which directly lowers the largest operating cost in pig production. In traditional farms, disease outbreaks can wipe out months or years of profit in a single event. While no system is risk-free, the controlled environment of the towers reduces the frequency and scale of such losses. Over time, this stability is what turns an unconventional structure into a financially viable operation, especially in a market where supply security has become just as important as price. Even with tight control and impressive output, this type of vertical pig farming is not without risk. One of the biggest challenges is system dependence. When production relies heavily on automation, sensors, and centralized control, technical failure becomes a serious vulnerability. Power outages, software errors, or equipment breakdowns can disrupt feeding, ventilation, or waste handling within hours. In a system housing tens of thousands of animals per floor, response time matters far more than in smaller, decentralized farms. Another risk lies in economic exposure. The upfront investment for projects like this reaches hundreds of millions of dollars. That capital must be recovered over many years, making the operation sensitive to prolonged downturns in pork prices or rising feed costs. If market conditions remain unfavorable for extended periods, financial pressure can build quickly, even if biological performance remains stable. Public perception is also an emerging issue. High-rise livestock farming raises ethical and environmental questions among consumers, especially outside China. Concerns about animal welfare, industrialized food systems, and environmental footprint could limit acceptance in some markets. These factors do not directly affect production but can influence regulation, investment, and long-term expansion. Despite these risks, the model has clear appeal in certain regions. Countries and cities with limited agricultural land, high population density, and strong demand for animal protein may find vertical farming economically attractive. Parts of East Asia, the Middle East, and even densely populated urban regions could adopt similar systems, particularly where land costs outweigh construction costs. However, success depends on access to cheap energy, strong biosecurity enforcement, and stable supply chains. The key question is not whether this model can replace traditional farming, but where it makes sense to exist alongside it. Vertical pig farming trades land and labor for capital and control. In some contexts, that trade-off is logical. In others, it may not be. What do you think? Is raising livestock in high-rise buildings a practical solution for future food security, or does it introduce new risks that outweigh the benefits? Share your thoughts in the comments. Thank you for watching. If you found this breakdown useful, don't forget to like the video, subscribe to the channel, and join us next time for another deep dive into how engineering is reshaping modern agriculture.